Hi. So, we will start from where we left off, which was the parallelism available in shader programs. As we know that these are basic data flow style of computation, and the primary work of shader programs is to model how light interacts with different materials and accordingly to render complex lighting and shadows. So, a typical shader program will kind of interact with several specific units that generate some specific components of a output graphics. So, for example, there would be the setup and rasterizer unit that would generate the pixel fragments that are kind of potential contributions to pixels and covered by a geometric primitive. The pixel shader program is the one that fills up the interior of the primitive. So, the first one generates the fragments to be covered by the geometric primitive. The interior will be kind of painted by the pixel shader program. So, that also gives a hint that this is the block which will be more compute intensive. It includes interpolating per fragment parameters, textures as well as coloring, and by raster operations we mean the stage where things like color blending, testing for stencil as well as depth testing, these are being done, right. And so, these are also specific units. If you look at the picture here, so you have the input assembler, the vertex work distributor, the pixel work distributor, and these units which are present in this block diagram, and they also nicely map to the graphics logical pipeline containing the input assembler, vertex shader, geometry shader, rasterizer, the pixel shader as well as the output merger phases. So, we overall I understand that for a specific shader program, we have the setup rasterizer unit, then the pixel shader program and the output merging or the output processing phase. So, we will see that how this kind of graphics processing nice map they will kind of nicely map to GPUs which support this massive multiple threaded computation. So, for GPUs the primary goal at its early age was to provide a solution which was partly programmable. It should be able to accelerate the working of this kind of a graphics pipeline. The reason being that you want the graphics to be rendered with as much resolution as possible, as fast at a high rate as possible. The higher rate at which you can render the graphics, the images would seem, the movements would seem that much realistic, right. So, the overall goal was to cover the latency of memory loads and texture fetches from the DRAM. So, in order to activate the graphics pipeline very frequently, you would like to fetch this data from the DRAM with that much high frequency as possible, or you have to fetch in a large width. That means, in each transaction you fetch a lot of data points and work on them in parallel, and that is how you can cover the latency of memory loads. This is what it means by covering the latency. And then comes the point that, well, you have fetched lot of data points for the graphics pipeline to work or the graphics shader programs to work, you should be able to work on them in parallel and do the compute, right. So, this helps to accelerate also general parallel compute programs, but the primary goal was to accelerate graphics shaders in parallel. The third goal was to virtualize physical processor as threads and thread blocks to provide transparent scalability. Now, this is an interesting point. You are trying to say that, see, parallelism is not a specialized thing, rather let us look at every operation as parallelized, think that that is the general case and try to accelerate parallel operations. That means, you always think in parallel, you start thinking that you have a thread of computation where every computation has the ability to work on parallel number of on a set of vectors instead of scalar points. So, with this design goals, this idea of GPU design started, and also the overall objective comprised that you should be able to simplify the parallel programming model by simply making a programmer write a serial code that's about what one thread of computation is going to do, and it's just that you write a sequential behavior of a single thread, and it's just the case that the thread works on multiple data points in parallel for doing all the operations sequentially. So, what were the first generation GPUs? So, this GeForce 256 was introduced in 1999. This was one of the first GPUs, and they contained fixed function vertex pixel shaders, which were programmed with OpenGL and Microsoft DX7 API. So, the graphics pipeline for this GPU still contained fixed function vertex and pixel shaders. That means they were not software programmable in the sense that they can be, these are hardware blocks which understood the lower level API calls from OpenGL and Microsoft DX7. Then came GeForce 3, and this was the first programmable vertex processor which was executing vertex shaders. So, what happened with them was these blocks of the graphics pipeline, the blocks highlighted in blue, that is the vertex shader, the geometry shader and pixel shader, they, instead of being fixed function blocks on the hardware, they became programmable blocks. That means the GPU will be having this general purpose programming interface through which it can run the vertex shader, also the geometry shader programs, also these pixel shader programs. So, for this and all subsequent many contents at many places, we will be referring to this nice paper that came up in IEEE Micro in the year 2008. The paper is titled NVIDIA Tesla, a unified graphics and computing architecture. So, one of the position papers on the Tesla architecture that was published at that point of time. Now, what was the trade-off that the designers of this Tesla architecture or the Tesla family of GPUs were really looking at? So, if you look at what is the activity of a vertex shader program, which was to be run earlier by vertex processors, as I said, the fixed functional blocks which would be part of the early GPUs or early graphics systems, that there would be a specific fixed function hardware block which will do vertex processing. There will be a fixed function block which will do the pixel shader processing and all that. So, for them, they had quite well defined objectives. The vertex processors will operate on coordinates, but they will implement high precision math operations at low latency. So, that was the design objective of a fixed function vertex processor. When it came to the pixel fragment processing, they were optimized for high latency, but low precision texture filtering. They are typically more busy considering large triangulations. So, if I consider large triangulation of an image, there will be lot of pixel points inside a specific triangle. So, processing at the pixel level will be having lot of compute load. For that, they need not be done at a high precision level, but the objective is to do more of them in parallel, right. Now, if these vertex and pixel processors are implemented as fixed function blocks, it is difficult to select a fixed processor ratio. That means, how much throughput should be allowed for the vertex processor and how much throughput should be allowed for the pixel processor, because that also, because overall how much this pipeline will work at what is the overall throughput, that also depends on the input data, input images triangulation scheme. So, if it's really as has been thought here, that is large triangulation, then the vertex processor will be operating on lesser number of points. So, this idea would hold that yes, it can work on lesser number of points, but compute in high precision, whereas the next level will have lot of things to do part triangle. So, they work on low precision, but however, the triangulation is considered in the input image as small. So, then the vertex processor will have lot of things to do, because there are lot of triangles in the input, lot of vertices to process, but for the pixel processor the part triangle job is reduced, right. So, if they are implemented in hardware as fixed function blocks, what is an ideal image scenario, that I mean the overall throughput of this sequence of fixed function blocks would actually be a function of how the input image has been triangulated and how it has been provided. The common case may get accelerated, but the cases which are not common may suffer from performance impediment, right. So, the primary design objective for the GPUs, the Tesla architectures was that they should be these different vertex pixel fragment shader programs. They need not be implemented as fixed function blocks, but they should be implemented uniformly on a programmable processor, such that the same processing fabric can be reused for both of them, so that it, depending on dynamically what is the input triangulation, it can be decided how many threads will be doing the computation for vertex processing and how many threads will be doing the computation for pixel processing, so that overall we have a very high throughput. Now, this unification helps in, as we have discussed, the dynamic load balancing of these varying throughputs of vertex and pixel processing, and it also helps in introducing many other possible shaders that can be part of the graphics pipeline. As we know, this is always the case when you move some hardware functionality to a software functionality. With increased programmability, you can do more dynamic load balancing of things. So, essentially you move out from these fixed function blocks, make them all part of a programmable parallel processor, that is the GPU, and you just dynamically decide how many threads will be computing for the vertex or the pixel, what is good for the overall high throughput functionality required. So, coming to this Tesla architecture, we speak of again this GeForce 8800 GPU with 128 SPs that are organized as 16 streaming multiprocessors or SMs. So, in this specific GPU, you have an external DRAM control, you have fixed function raster operation processors ROPs, which perform color and depth frame buffer operations directly on the memory. So, given that you have these ROPs present, it is possible that to do these specific operations on color and frame buffer depth directly on memory, instead of bringing them for doing some compute on the main processor pipeline. The interconnection network carries these computed pixel fragments, colors and depth values from the SPs to the ROPs. So, just to get a feeling of the connectivity, if we look back here into the picture that we had for our GPU. So, we have these ROPs being connected with the interconnection network, and also so the interconnection network is here connecting the different TPCs which contain the SMs and also the SPs, and this interconnection network also connects the ROPs, and they connect the DRAMs through this hierarchy of level 2 caches. Now, coming to our point here, so this external DRAM control and the ROPs, they perform color and depth frame buffer operations directly on the memory. The interconnection network carries the computed pixel fragment colors. So, they carry the output pixel fragment colors and depth values from the scalar processors to the ROPs for doing the fixed function raster operation, and then they get stored back to the memory. The network also routes texture memory read requests from the scalar processors to the DRAM, and they read data from the DRAM through a level 2 cache back to the SPs. So, this ROPs, that is the raster operation processors, they still remain as fixed function blocks, and they do their operations and they store back the data to the memory back and forth through the hierarchy of L2 caches, and the interconnection network carries this computed pixel fragment colors and depth values back from SPs to the ROPs back, right. So, coming to the graphics in the Tesla, what are the different blocks that are present in the architecture. So, first of all there is the input assembler which collects the vertex work to be done, and then you have the vertex work distributor that distributes this work packets to the different TPCs that are present, and these TPCs are going to execute the final shader programs, both the vertex as well as the geometry shaders. Now, this is where, as we have also already spoken, that the programmability comes in. Earlier vertex and geometry shaders also used to be fixed function blocks, but now they become a part of the programmable pipeline. So, with this, just to finalize once again, you have these raster operations still in fixed function blocks. The data flows between these raster, these ROPs and the DRAM through this level 2 hierarchy, and the interconnection network will carry the fixed fragment colors and depths from the SPs to the ROPs for doing the raster operations. Of course, the SPs are there to execute the different shader operations, and coming back here, the TPCs will execute these shader operations and the output data will be written to the on-chip buffers, which will further be passing the result to the viewport or the raster block. So, this is how, as we can see, that the original graphics pipeline gets represented in the Tesla architecture, with the shader operations being done in the scalar processors, whereas you have the raster operations being done in the fixed function blocks, and also the buffers, the overall outputs are written to on-chip buffers and they pass the result to the viewport. So, this gives us a basic idea of how graphics processing changed from fixed function pipeline to a GPU pipeline, and from here we will continue to how GPUs in general handle instruction processing in more in the SIMD style, and we will talk about general purpose programs. Coming back to the way the different functional units would be arranged in the GPU. So, you have each of these TPCs, they contain 2 streaming multiprocessors. Each of the streaming multiprocessors have got 8 streaming or scalar processors. So, these scalar processors along with them these SMs will also have 2 special function units or the SFUs, and there is a multi-threaded instruction fetch and issue unit. So, again if we just go back to this figure. So, this is since we have already back. So, as you can see, we have this input assembler like we discussed for the graphics pipeline, then the vertex work distribution which will distribute work, and also the pixel work distribution, they distribute the vertex and pixel works to the different TPCs, and finally, we have the ROPs as fixed function blocks, also the texture units as fixed function blocks, and the outputs finally go to the viewport. Now, coming here to the internal content of each of the streaming multiprocessors. So, you have the iCache for the instruction fetching instructions, and then you have this multi-threaded issue unit which is going to issue instructions in parallel to each of these scalar processors or streaming processors. So, as we have discussed, this each SM has got 8 scalar processors and also 2 special function units or SFUs. So, this multi-threaded instruction fetch and issue unit is supposed to issue the instructions that are going to be executed by the scalar cores, and also as we have seen in that picture, we have a 16 KB read write shared memory as part of each streaming multiprocessor. So, what is there inside each of these streaming multiprocessors? In summary, each SP core will contain a scalar multiply add unit. Thus, that would mean inside each streaming multiprocessor you have got 8 scalar multiply and add units. Also, the SM, as we have seen, it has got 2 of the special function units, and these special function units can be used for doing some transcendental computation. Also, each of these SFUs contain 4 floating point multipliers. So, overall I can say that inside each this streaming multiprocessor I have got 8 multiply and add units and also 8 floating point multipliers. I can do 8 floating point multiplication operation in parallel and also 8 scalar multiply operations in parallel. Now, coming to the execution model. So, as we have seen, this idea of data parallel computation by instructions is well known as a single instruction multiple data. This is the idea, I mean, which emanated also from vector processing, and this idea gets much more generalized when people thought of the execution model for GPUs. So, what people started talking about is single instruction multiple threads. So, that would mean that you have multiple threads of computation, or in a different way I would say that I have a single thread of computation. It is executing a sequence of instructions. Each instruction is working on multiple parallel vector type data points. So, looking at the other way, I can just say that okay, since I have a single instruction processing, but it is doing the same job for different parallel threads of execution. So, that gives me that idea of what is SIMT, that is instead of saying single instruction on multiple data, if those data points all belong to parallel threads which are making progress in parallel, I would start calling them single instruction multiple threads. So, with single instruction multiple threads, I have a more generic model of instruction processing, because essentially what I am saying that okay, to let's just take a simple example here. So, when I am executing a sequence of vector instructions, in general they may be related, they may be unrelated. That means, well, they can be doing computation towards a similar objective, or they may not be doing so, right. I mean, it depends on how the processor has figured out the parallelism, and it has found that okay, I have multiple vectorized instructions, I can process them in parallel and all that. But now suppose I say that okay, I have multiple threads of execution. So, this is thread 1, this is thread 2 and this is thread 3, and I say that all the threads are going to do an add operation here, and then all the threads are going to do some subtract operation here, and then all the threads are going to do some mult operation here. This is the demand of the program. When I say that, looking at it from another way, I can start saying that okay, for this you need an SIMD instruction, because well, you are looking to do an add.v processing, this is the vector processing, but when can it do that? Only if the work for each of the threads are such that they are similar. This thread also needs to do an add, this thread also needs to do an add, this thread also needs to do an add. Once that is done, this thread will do a sub, this thread will do a sub, and this thread will do a sub. And not only that, when this thread is doing the add and the next thread is also doing the add, they are doing the add on consecutive items, they are all doing the work on specific vectors. So, just when I start looking at a program where all instructions are vectorized, it is not that I have a program which is basically a scalar program, and for extracting parallelism purpose, the compiler had figured out that okay, here something is done in parallel, and then again there is some vector processing that can be done. It is not like that. We are going to generalize this concept, and we are starting to say that no, the entire program is like a vectorized operation. Just start looking at it in a way that with each operation you have a set of threads that are making progress. Then I can say that I have a sequence of this kind of instructions, a single instruction which is operating on multiple threads. Once that is done, again I have another such instruction which will again operate on multiple threads, and that is how the computation progresses. So, coming to SIMT, instead of starting to think, just doing a basic summary again, because this is the most important thing here. Instead of saying that okay, it is not that you are doing some program execution where some part of the code is scalar, some part of the code the compiler has identified to be data parallel, and hence this has executed, it has emitted some vector instructions. Let us generalize that. Let us think that every instruction execution is of some type vector, and not only that, the entire sequence of instructions is such that they represent the progress together by multiple parallel threads of computation. When we start talking like that, we mean that okay, we are thinking of a programming model where I have a sequence of instructions which is such that every instruction is like an SIMD instruction, because and not only that, every instruction is doing an SIMD operation which is part of some set collection of threads. Then again there is another SIMD instruction which is again making progress with the operation for that specific collection of threads, and in that way things are going on. So, in that way what we have is a nice data parallel program, and that data parallel program has got multiple threads of computation, and they are all being executed synchronously by a sequence of instructions. Alternatively, I can look at it just like this, that okay, I have a single thread of execution, but in each point of execution is working on multiple different data points. So, just to make things very clear and not to get confused, I can say that these two pictures are quite equivalent. I have two threads which are executing like this, but whatever they do here, there is an add on vectors. So, there is vector component v1, vector component v11 and v11 v11 and v12, and then again so this is the first operand, and then there is some second operand, they are doing an add here, then again they are doing some other op, then they are doing some other operation like that. So, I can say that I have a sequence of SIMD operations going on multiple different threads in parallel. Alternatively, I can say that I have data sitting in vector data types. There is one thread which is going on and doing a computation on them, producing a result, and then again it is doing a computation on some other vectors and again producing a result. Well, there may be dependencies and all that. So, it is less like thinking that I have a single thread which is making progress doing operations on parallel data vectors, or I can think that I have in that way I have multiple threads which are making progress in parallel. But both of these pictures at the instruction level maps to a scenario that I have a vector instruction which is doing computation for different data points belonging to these different threads, followed by another vector instruction doing some other computation to this same set of threads, and they are overall making some progress. So, just the summary is that when I speak of SIMT, I can say that it is about one instruction getting applied to multiple independent threads in parallel, not just multiple data lengths, and the one SIMD instruction controls a vector of multiple data lengths together, whereas an SIMT instruction controls the execution and branching behavior of one thread. So, this may sound confusing, but this is what it means. When I talk about SIMD instruction, it controls a vector of multiple data lengths together. So, you have vector data type sitting the type of data sitting on multiple data lengths, and the same SIMD instruction is operating on them, right. When I say SIMT, it controls the execution and branching behavior of one thread, because when there is a branching happening, these different threads may have different behaviors. That is why you have this instruction which would mean something for one of the threads, but it may mean something else. It may be I have one SIMT instruction which may mean something for one thread, but it is essentially also going to mean something completely else, a different branching style for some other thread. This is something we will explain in more detail later on. For the time being, just remember those two pictures that we are discussing, that overall the idea is very simple. When I talk about SIMT, is just like saying that, well, let us generalize this concept of single instruction multiple data and start thinking that you have instructions operating across multiple programs or their lightweight versions, that is threads, and all the threads are making progress in lockstep. That means fundamentally all your instructions are SIMDs. So, you have one SIMD instruction operating on different program threads, again another SIMD instruction operating on different program threads, so on and so forth, and this is how it keeps on continuing. So, in contrast with SIMD vector, SIMT will enable programmers to write thread level parallel code for independent threads as well as a data parallel code for coordinated threads. Let us understand what we mean. So, as we have said, this is SIMT, that means a single instruction working across multiple threads. But when you look at the behavior of the program, you have multiple threads, but you need to specify the functionality of only one thread, how that thread works for its data points and all that, right. So, I can say that it enables the programmer to write the thread level parallel code for one thread. If different threads are supposed to do different jobs, then there will be some more complex code to write, which we will see that how that works, but ideally you are going to write a per thread behavior, and that is going to be replicated across the different parts of the different parts of the data segment. So, in that way I can say that it is essentially a single thread of SIMD instructions. So, that is the alternate view I was speaking of, that I have essentially a single thread of execution, but all the instructions are executing as SIMDs. So, each of these streaming multiprocessors multi-threaded instruction unit, they are going to create, manage and schedule and execute threads. So, they will spawn the threads, they will manage their execution, they will map them to the real hardware, that is the scalar processors or SPs, and finally they will say that, okay, these are the threads that have executed, they have committed, and these are the threads that I have to start and all that. So, this multi-threaded instruction unit that we showed in the last picture, this is the thing that is going to do this. This is also known as the hardware scheduler. We will talk about that again later on. But the important thing is this management of threads are done in blocks of 32. 32 threads together are packed as something that is called a warp. So, this is a basic atomic unit of parallel execution in a GPU. So, when I say that it is a warp, that I mean that I have 32 parallel threads, they together are making progress in the SPs. So, when a warp makes progress from some by executing an add instruction, that means all those 32 parallel threads have executed the add instruction. Each SM, now this is specific to that architecture that we have been talking about, it manages a pool of 24 warps with a total of 768 threads. Now, again this is specific to the GeForce architecture. Each SM maps warps threads to the SP cores. So, as we can see that there are lot many threads to manage. So, essentially there are 768 threads, they are being distributed across 24 warps. So, 768 if you divide by 32, you get 24 warps, but each SM will map these warps to the SP cores. How that is done is also the job of the SM. Now, of course, again I will just repeat, these are the numbers that are specific to the GPU architecture we have been talking about. With different GPU cards, these numbers keep on changing and they become much bigger with modern GPUs. So, execution of warps. In each operation cycle, the SM warp scheduler will select one of these 24 warps. This is again just a synthetic example. I have 24 warps, one of them will be picked up, and for in each cycle of activation of the SM's warp scheduler, it will select one of these 24 and map it to its SPs, so that the SPs can process that warp. An issued warp executes over 4 processor cycles. The SP cores and SFU units execute instructions independently. Of course, the SP cores have got the scalar multiply and add units, 8 of them, and SFU units, which are again 8 of which contain, and there are 2 SFU units in each SM, and they contain in total 8 floating point multiply and add units. So, they are operating independently. So, with this we will stop here and we will start again with more details of how the SPs execute the warps in the next lecture. Thank you.